work? Yes. So I guess let's start. So welcome to this second tutorial. And again, today we will have two exercises. And the first is precisely concerned with this formula. So Francesco showed during Wednesday lectures that there is some thermodynamic potential, a current associated with the logarithm of the partition function. In particular, we have and in this case, we want to see who is this phi mu. And we'll see that phi mu is in fact the pressure times beta mu. To see this, there are basically two methods. The first one, let's say, requires some thermodynamics. And it's based on a formula Francesco gave during the lecture, which is this one. Phi mu is the integral between 1 and infinity in the lambda of the expectation value of the energy momentum tensor lambda beta nu, where these expectation values with this lambda subscript is computed using the density, a modified density operator, which is 1 over z the exponential minus lambda. So using this trick, redefining the density operator like this, and rescaling the temperature basically by this parameter lambda, Francesco was able to obtain this formula. And now we are using, in the first stage, we will use this formula to find phi mu. And also we will use a result we discussed the other lecture, which is that in particular now we will be interested in the case of global equilibrium with homogeneous temperature. So in fact our density operator is 1 over z e to the minus beta dot p, where beta is a constant. So last time we have seen that in this case, with this density operator, the energy momentum tensor assumes a simple form, which is the ideal hydrodynamic one. So we can use this result in this case, but since we have a modified density operator, now the thermodynamic function pressure and energy density will not depend only on T, but in fact they will be functions of lambda. So lambda, and some lambda. Okay, so if we use this formula, recalling that beta mu is the ratio between the for velocity and the temperature, we can see that phi mu is just the integral between 1 and infinity of only the energy density as a function of lambda, because here we can you can realize that this is the projector orthogonal to the for velocity. And so in fact here we get the energy density lambda times beta mu. Now beta mu is a constant, doesn't depend on lambda or anything like that. So we have seen that we see already that phi mu is given by beta mu times some function phi, which is defined by this integral. And yes, that's it. Exactly. Now that we have derived this relation, we can basically get to the thermodynamic relation. We need to prove that phi is the pressure. In fact, we need to realize that epsilon is not a function only of lambda because of the form of the density operator. So again, using this density operator together with the definition of the for temperature vector, you can see that this, whenever there is lambda, there is also over t attached to it. So this is a function of lambda over t, not of a lambda only. Therefore, we can change name of the variable inside the integral, and we can write this as the integral of t times the integral this lambda over t epsilon of lambda over t 1 at infinity, and this basically means that we have an integral between 1 over t dx and energy of x. What? I changed, this was integral in lambda. Yeah, maybe this, let me write like this. So this was an intermediate step, and now I changed from lambda to lambda over t. So when lambda is 1, x is 1 over t. Yeah, so I am changing the integration variable. And now let's see what happens if we compute the derivative of phi over temperature. This is equal to, the first part is easy, it's just the integral, which means is phi over t. And the second part is just the fundamental theorem of calculus. We have epsilon at infinity, at lambda equal infinity, this is an x, which is 0 because lambda equal infinity means beta equals 0, basically, or, yeah, sorry, temperature equals 0. And minus the energy density computed at the standard temperature times the derivative of this guy. So it's minus 1 over t squared epsilon times t. And so we find that t times the derivative of d phi over t is equal to epsilon, sorry, there is an additional minus because it's infinity minus 1 over the derivative in 1 over t, so it's plus here. And we find this relation. And if we now know some thermodynamic relation, we can realize that this is true if the thermodynamic function phi is equal to the pressure. And this reproduces some Gibbs relation from thermodynamics. But this requires the knowledge of thermodynamics, and we can derive the same conclusion from another method, which I will show you now. And that starts precisely with the very definition of the phi current. So we have this relation. This is equal to the logarithm of z. Now, z on the other hand is just the trace of that exponential operator of the energy density. Oh, sorry, of the density operator. So we have.
So this phi you are starting from x, the same phi we have in the expression of entropy kinetics.
Yes.
So in the class, I don't know whether I get it correctly. It was written from lambda 0 to 1. Why it is 1 to
From lambda 0 to 1. I mean, so this relation comes from this trick, and then you have to, basically you need to find two values of lambda, one of which is such that the partition function computed with the scale density operator at that lambda vanishes, and the other one is a lambda 0. You can put it to a lambda 0. But then, I mean, you would get basically you get something like logarithm of lambda 1 minus logarithm of lambda 0 equals to some integral, probably that one. Yes, and there is an additional integral here. So this is, I guess, sorry, this logarithm of z at lambda 1 minus logarithm of z at lambda 0. And I guess there is a minus here because of the density operator. So basically, since in fact you're not interested with this density operator, but the one with the 1 here, so you have, if you put infinity at lambda 1, this guy goes to 0 because this is temperature equal to 0. And lambda 0 equal to 1 gives you the right partition function you want. So that's why there is a 1 there and not lambda 0. But in principle, yes, it's true for, you can, I mean, you can compute this at any lambda 0. It's just that you're not interested in that. Again, but I will, this is by memory, I don't remember. I think it's like that, but I will double check later. So as I was saying, here we have the trace of e to the minus beta dot p. Now, if we take this relation, we can compute, for example, the derivative with respect to beta mu of our logarithm of the partition function. Let's put also a minus sign for convenience. And if we take a look at this part, we realize that this is just p, sorry, the trace and this here is just the partition function itself. So here we have reconstructed the density operator, and it means that the derivative of the logarithm of z with respect to beta is the expectation value of p mu. Now, in order to compare this left-hand side of the equation with this guy, we also want an integral over some hypersurface here. But this is easy to achieve because we know that the form momentum operator is a global charge and is the integral of the energy momentum tensor. So we have this relation. Okay, so these hypersurfaces are any kind of, are arbitrary. So we can say that the integrands are equal. In fact, there could be some additional term. For example, we could have, maybe, yeah, I'll keep it like that. So we would like to do the following identification. We would like to say minus d phi over d beta mu is equal to t mu nu, expectation value. In fact, as I was saying, there could be something that, because of boundary condition or for some reason, vanishes when integrated on any hypersurface. For instance, by the Stokes theorem, you can see that if phi goes to phi mu goes to phi mu plus some derivative, I mean, actually, this could be, let's put it like this. There could be something going like mu nu, where these two indices are antisymmetric. And by Stokes' theorem, one can move this integral to an integral over the boundary of the surface. And if there are some boundary condition fulfilled, the integral will be 0. But we are in a lucky case, because in the case of global equilibrium with homogeneous temperature, any gradient is 0 due to translational invariance, which is something that I should have shown you last time, but I didn't, so I will do it now. So why gradients are 0 at global equilibrium with a constant temperature? This is very important. For example, let's consider the expectation value of some operator O, which is an operator of x. So we have rho of x. We have to keep in mind that translations as operator are generated by the four momentum operator. So a translation of a vector alpha, let's say, is given by this kind of operator, minus I alpha. Alpha is some vector, p. But now, since we are in this simple case of a constant temperature, we have that rho, which is again e to the minus b dot p over z, is such that it commutes with t. Because of course, translation form an abelian algebra. Therefore, if I call this guy just O of x, I can write O of x is equal to the trace of rho t alpha minus 1 t alpha O of x. So I did nothing, this is just 1. But then I can commute rho with t and use the cyclicity of the trace to get the t minus 1 on this side of the trace. This is equal to the trace rho t alpha like that. And these guys are the translation operators, and it means that this is just the operator O evaluated at the point x plus alpha. And we have shown that O of x is equal to O of x plus alpha for any alpha. And it means that O does not depend on the space-time point. Let's just remove this. Okay, so since gradients are 0, this is gone, and we are left with t mu nu is equal to minus the derivative of phi nu with respect of beta mu, right? Yes. With this relation. Again, I just erase it. So we will need again that t mu nu has this form. And now, since we are concerned with this kind of equilibrium, again we can, the only vectors we have at our disposal to write a phi mu vector are, well, is only beta mu. So the only way we can write phi mu is beta mu times some function, which is a function of the scalars at our disposal, which are just beta square. So we would have something like that. And now we are basically done, because we have to compute this derivative. We find t mu nu is equal to minus phi of square root of beta square. And then we have plus beta mu. And we have the derivative of this guy. So it's beta nu over square root of beta square, derivative of phi with respect to the square root of beta square. And this is equal to minus phi. This is, this is a minus, exactly. So this is minus 1 over t square, or beta square, basically. And you can realize that this boils down to, so we would get beta mu beta nu. Then we have this 1 over beta square I call t. Then we have a beta squared down here. And then we have the derivative of phi with respect to t. And basically, here I forgot g mu nu. Sorry about that. Let me write that. So now, comparing this expression with the one above, we reach the same conclusion. In particular, from the g part, we see that phi is equal to p. And this time, we derived this relation by this method. So we see that t derivative of phi with respect to t is equal to epsilon plus p, where p now is phi, as before. So we have found the same conclusion as before, but with a complete derivation, let's say. And this was the first exercise. Questions?
So in the second derivation, you had to use the fact that the global equilibrium is gradients vanish.
Yes.
How does it manifest itself in the first derivation?
How does it manifest itself?
Yeah. So supposing the same faction is also somehow hidden in the first derivation.
The first part in the first derivation. I think at some point, I believe it was needed that beta is a constant. I think at some point we used that beta does not depend on lambda. That maybe is the point where you need it. Let me think about it. Epsilon. Yeah, actually, it's not. So at some point we use that epsilon is a function of temperature only, basically. If we, I mean, or of lambda over t, exactly. If you had, for example, equilibrium with rotation, so in that case the gradient of beta are not zero, but in that case you also have epsilon is also a function of vorticity, for example. So that step would not be accurate in that case. Yeah, good question. Other questions? Okay. Then the second exercise is, on the other hand, concerned with the vigner function, which Francesco introduced today. And I know some of you are familiar with this concept, but I bet not every one of you. So I will first of all like to show you why the vigner function is defined in that way, because Francesco kind of declared that it was like that. And then we will see, we will try to compute the vigner function in this very same kind of equilibrium. And this exercise will also be useful, hopefully, for those of you who wants to take the exam. I think there are some people, don't know if they are here. So the vigner function, and we will discuss the Dirac field, the case of Dirac field. So in this case, the vigner function is defined like this. Where, well, psi bar is just... Okay. And this is in general a function of x and k, these two variables. Now, I want you to realize... yes, this is a minus. I will put it out. this is a minus. So this is a 4x4 matrix with spinor indices. And the key thing to keep in mind is that this is an auxiliary function. It's not really something physical. It's just something useful to compute expectation values. So where does this definition come from? Let's, for example, suppose we want to compute the mean current like this. Here we have, sorry, here there is an expectation value, otherwise it's an operator. So this is the Dirac current. And now, basically, what we are going to do is to insert 1 in a very fancy way in order to get an expression involving the vigner function. So first of all, here I have a normal ordering in order to remove the infinities coming from the vacuum. And first of all, I can realize this is a product between spinor matrix and spinor. So I can also write sum over AB, and then I have expectation value psi A So I just wrote explicitly this product. I can now move around the elements of the product because the sum is now explicit, and I can exchange these two guys, keeping in mind that they are Grassmann variables, and you have a...
If you define the vigner function using the normal order,
Mm-hmm.
then you should remove the minus sign. Because you're using the minus sign when you change the order.
Yeah, but now I will.
But now you have the normal order.
Mm-hmm. Yeah. Yeah. Okay. I'm not sure, okay. So, going on, now we can rewrite this part, exchanging psi and psi bar. And we have sum over AB. Come on here. Yeah, I think it's because of the normal ordering, but I'm not fully convinced. Are you sure that there isn't a minus sign?
Normal ordering is
Okay.
you always put
Yeah. Okay, so it's the same. But if I didn't, but I'm confused. Okay, I will have to check. But I trust you, Xinli. So it's a problem with the normal ordering. Without the normal ordering, there is I guess a sign to pay in when you exchange psi and psi bar, and with the normal ordering you don't pay the sign, and that's why I messed up with the sign here. Yeah, exactly. Exactly. So are you sure that there isn't the sign? I think. Because these are Grassmann. Yep.
Because cyber also has a creation operator, also has an annihilation operator, different compared to cyber. So it doesn't, I mean, normal ordering will automatically take care of the fact that...
Yeah, but they anti-commute, so the...
But cyber is not creation operator. Cyber is, I mean, I don't know, antiparticle field maybe. It also has a creation operator and an annihilation operator.
I think it depends on whether you consider the particle or other particle. That's the full one. Maybe
that's the full one, yes. But no, I don't remember the thing. But in normal ordering, psi and psi bar anti-commuting, they get the minus sign. They get.
I think they get a minus.
Then there is a minus sign here. Can you check on the growth, David? Thank you. Because at this point, here I exchange psi and psi bar. So there should be an additional minus because they are Grassmann variables. And so here I get psi minus psi x b psi bar x a within the normal ordering. And now what I do is just I insert a delta function, which I also integrate out. So this is equal to the integral d for k 1 over 2 pi to the 4 minus I forgot the summation. Sum AB. Yes. Okay. So from here, we get this thing, which is just the Wigner function I have defined, and an additional integral. So we see that we can write the current like the integral d for k, the trace of gamma mu w, where I have used I've written the sum over a and b as the trace, because here we have a cyclic sum. Has a minus sign. Okay. Anyway, but see, you see, this is also a kind of a convention. For example, here I've put minus, but by the same argument I could have put a plus. I could have also written this with a minus in front and an additional minus to the Wigner function. It's also a matter of convention. Again, think about the Wigner function as a tool, not really a physical quantity or something with an inherent meaning. Or so. Yeah, but nice is an arbitrary concept. Yeah. Yes. Okay. How do you, sorry, I can't hear you.
How you can get the second class time from the I mean, there's D4
From here to here.
Yeah.
Okay. You see, I've put an integral over k and an integral over y. If I switch them and I integrate over k before, this is just a delta 4 of y. So it forced me to compute this guy at y equals 0. And I get back to here. I've basically put plus y minus y here, but with a delta of y. So maybe I can do an intermediate step. Actually, this would be helpful. This is just delta 4 of y. And then I have gamma AB. And then minus. And then I have psi So exactly. So I basically did nothing, but I did this step in order to get this d4k integral here. So instead of computing the trace with the density operator and so on, if somebody gives me the Wigner function, I can compute one integral, and I'm done. And now our next task is indeed to give you a Wigner function. Yes. So we will use this definition, And of course, at some point, we have to compute the trace with the density operator. There is no free lunch, as the theorem says. So I will focus only on the particle part, but there is, as Francesco said, you can decompose these in a particle, antiparticle, and a space-time part, basically simply by expanding our field, D3P. And then since we are in the Dirac case, we have P, we have a sum over the spins, S, U, S, P. Now, if we plug the full expansion there, we can see there is a part that goes like A dagger A, which is the particle part. Then we will have something going like B dagger B, antiparticle. And then there are some mixed terms. And these will give you the decomposition into space, particle, antiparticle, and space-like parts. But for the time being, we focus only on the particle part. So we can, delete this. Of course, it's there, but we are not concerned with it. So now it's just a matter of algebra, basically. We have W equals 1 over minus 1 over 2 pi to the 4. And then integral D for Y e to the and then we can put 1 over 2 pi to the 3 integral d3p okay, then we have the spinors. Let's write u s, let's write the sum over s and r of u s of p, u bar r of p prime. We have e to the minus I p x minus y half e to the minus plus p prime. Here we have a plus because it is psi bar, and that's also why we have a u bar here. X plus y half. And then finally we have the expectation value of a s p a dagger r p prime. This is in normal ordering, so I will pay a sign and change the order. So I get r. Now, okay, let me write it explicitly. So this guy is equal to minus a dagger r p prime a s p. Okay. I hope I didn't forget any factors. Okay. At this point, this is the moment where we have to compute the trace with the density operator. And we have to compute the expectation value, basically, of the number operator with these two different momenta. So we have to compute the trace of e to the minus b dot p over z, a dagger r. So I think Francesco did this for the Bose gas today in class. And it basically told you the result. For the Dirac case, this is just this thing here. Now, however, so this P minus P prime, and then we have the Fermi distribution. So do you actually, do you know how to derive this? Do you want me to do it? Or I can give it as granted and go on? Huh? Yes, very well. So the way to derive this relation is based on the translation rules of the creation and annihilation operators. So we know, okay, we have seen that on a operator in the position space, the translation acts like this. But what does it do on a dagger, for example? So a dagger R is the creation operator of a state with momentum p. It means that if we compute this, we get a state with momentum p and spin r. But we also know that our Hilbert space is built in such a way that p mu as the operator is diagonal over this state. And so we can try to guess what happens to A dagger once we compute this quantity, A minus, or just some random vector. Let's do it like this. Basically, this is the quantity that appears in our trace. So using basically these properties of the Hilbert space, we can write this like that. So we just put an identity on this other side, B, P minus B, P. And now we have to deal with this quantity. Now, since basically the transformation rules of this follows from this property here, and in fact, if I compute E to the minus B, P acting on a state with definite momentum, this is E to the minus B, P, the eigenvalue here, over PR. But this is just this quantity here. And since the vacuum is translational invariant, I can also write this as from here, let's say. This is equal to E to the minus B, P, A dagger, R, P, E to the B, P, E to the minus BP, omega. And this is just E to the minus B. Sorry, I had to put the hats, otherwise it's not clear. BP and A dagger RP. So omega. So by comparing these two expressions, noticing that, as I said, the vacuum is invariant, so this is just omega again, we have that translation operator acting on the creation operator just gives us an exponential of the eigenvalue p. Therefore, maybe I write it there. Therefore, we needed to compute e to the minus b p over z, a dagger r p. And here there would be an a, but I will again put 1. So b p e to the minus b p. And then we have a s p prime. Now we have found that this is just an exponential, just a number. And this gives us e to the minus b p times the trace of a dagger r p e to the minus b p over z a s p prime. So you see, by this trick, we have been able to reconstruct the density operator here. This is just our row. And we have found that a dagger r of p s p prime is in fact equal to, using the cyclicity of the trace, the expectation value of as p prime a dagger p. And I forgot a normal ordering everywhere. Ah, no, sorry. No. Now, at this point, we know that A and I dagger anti-commute. So AS P A dagger P prime, sorry, the other way around, AS P prime P R. This is equal to 2 epsilon delta RS delta 3 P minus P prime, where the 2 epsilon delta is such that the anti-commutator is Lorentz invariant, which we like. And therefore, we can write this thing. Sorry, I forgot also the exponential factor. Nothing would work otherwise. So we find this expression to be equal to e to the minus b p. And then we have a dagger r p a s p prime plus 2 epsilon delta r s delta 3 p minus p prime. So we have found the same guy here. And we can just solve this expression for a dagger a. And you will find that a dagger r p is equal to 2 epsilon you will find this if you invert this.
A dagger R P A S P prime will have a minus sign. Then only you can take that side and it will become.
What? Where is the minus sign?
So that is anti-commutator.
Yeah, so a dagger a plus, yes.
So that's why the class has come in the denominator.
Yeah. True. Thank you. Okay. And okay, so from this relation, you can also see that, in fact, this number operator with 2 different spin indices is, in fact, trivial in the spin space. And that's why you also don't get any polarization or spin-related business with this simple case of equilibrium. But now we have all the ingredients. Yes. So for example, here you see that using this density operator with a constant temperature, we find some function, okay, Fermi-Dirac, very nice. But in the spin sector, so concerning the indices R and S, this is just the identity. So if you want to build, for example, Francesco defined during the lectures the spin density matrix, which I will write here, I guess. Spin density matrix is defined like this: Rs of P, a dagger R. Actually, I think this is S, P, A, R. So So these are the spin density metrics which we use for polarization purposes if you want to compute average spin vectors or the alignment or whatnot. And you see that in this case of equilibrium, this delta Rs makes this trace being trivial. There is a ratio of delta functions, but luckily they are the same delta functions, so we can simplify them very physics-wise. And basically this reduces to 1 over 2 delta Rs. Because the numerator and the denominator are the same, here is just the sum, this is the trace of the identity, so it's 2, and this is a number. So this is why you don't get any spin effects in or global equilibrium with homogeneous temperature. Whereas if you put, for example, a non-vanishing vorticity, you can see that this line of reasoning must be modified. You get a much more involved expression, and this thing is not zero. It's not the identity anymore. It becomes some nasty thing. Okay. At this point, I will continue here since it kind of makes sense. So I will delete this. Now we are basically done. So this is 2 epsilon delta Rs delta 3 p minus p prime Fermi distribution. And if we plug that expression here, we get the minus sign that was here simplifies the minus in the Wigner function. So we have 1 over 2 pi to the 4. Then we have the integral d for y. Very nice. So this 1 over 2. Now I integrate out p prime using this delta function. d3p over 4 epsilon squared. Then we have the sum, but now R and S are the same, so it's just sum over R. U, S, U, R, P, U bar, R, P. Also the exponentials simplify a lot because P and P prime are the same, therefore there is no dependence on X, and this is something we should have expected from before because I've shown that in the case of equilibrium with a constant temperature, quantities are independent on the space-time point, so it makes sense that our Wigner function does not depend on X, in fact. And we just have e to the minus e p, plus y. And finally, 2 epsilon Fermi-Dirac distribution. Yes, precisely. Now we can collect these 2 exponentials, and we see that we can build another delta function. So we have w equal to the 1 over 2 pi cube, the integral d3p I for, yeah, these guys also simplify, but okay. 2 epsilon. Then we have the delta function of k minus p, delta 4. And this is just p slash plus m. If I remember correctly, should be that, yes. And then we have the Fermi-Dirac distribution. And now we are done because this is just the invariant measure. This is the integral in d for p theta of p0, and we have the momentum goes on shell, and therefore we can use this integration here to remove this delta 4, and we get that the Wigner function is 1 over 2 pi cube. Then we have p slash, I mean, we can also put that theta of p0 delta And then we have p slash plus m. And this is the result. Again, you see that in this case, Francesco told you during class that K is a pseudo momentum, needs not be on shell in general, but in fact, in this case of trivial equilibrium, the momentum goes on shell. This theta appears because, as I told you in the beginning, I only computed the particle part of the vigner function. So this tells me that indeed this is the particle part because the energy is positive. If I had I computed the other part with the b dagger b, I would have got the minus here. What? Mm-hmm. The integral, I rewrote the integral like this with an integral in d for p, and then yes, I should put k, sorry. Yeah, thank you. This is w of k, and these are all k's, right. This kappa slash, okay. Yep. Okay, and basically we are done. So this is the vigner function. As I said, this can be used, for example, to compute the average current or from it the spectra. By the way, I had to mention that during the lecture there was a typo, I think, in Francesco's slide, and there was a wrong formula for the spectrum. So I will write it here. And but I think he already updated the slides, so I don't know if you can. Probably you will find them somewhere on the website. But the correct formula, which I don't remember, of course, is. Let me check. It's this one. So I think in the formula he wrote there was a gamma mu here instead of a p mu. This formula basically comes from this very formula, so the formula for the current. You get the number of particles by the integrating the current, because it's the global charge associated to the current. And with some manipulation, you end up with this formula. So if you want the reference, this is in this paper 2004.04650. But this requires some manipulation, so I don't have time to show you. And that's it. So, any questions about this calculation or anything in general? Okay, if not, then I guess we have the break, and then there are the talks. Thank you.